Uh, my name is Tyler Matson. I'm Tyler Matson.
I'm David Erlinger.
I'm Jack Galley, and this is our Project 1 helicopter motion.
For the sense making of equations, we have our known variables. Time initial is negative t, time final is positive t, and alpha and beta are constants. And then another known variable is d, also known as distance traveled, and our unknown variable is t. The assumptions we decided to make for this problem is gravity and air resistance could possibly be represented in alpha and as well as beta, and helicopters rest at time initial or time minus t and lands at time positive t. For our change in our x function, we found this by taking the integral to the position function of it and plugging in time initial to the x component of it, and this represents the distance traveled in the x direction. For our change in y, we took the integral to the position function and plugged in time initial into the y component, which represents the traveled in the y direction. And for change in time, this represents the total time, and this is from the distance in the x direction formula. Our units we decided that for the end, whereas the change in x and the change in y are in meters and time is in seconds.
Okay, for sense making of variables, beginning with alpha, we can see in the top left where alpha appears as a scalar in the acceleration in the y direction. And if we look at the graph of this acceleration, we can see that when the rover lands, it has a negative acceleration. So this is where we determine that A must be some gravity or innate downward acceleration on the helicopter, or else it would it would fly off and physics would break and things like that. Similarly, for the acceleration in the x direction, it also appears just as a multiplier to the function. And if we could see in the graph of that we also have a negative acceleration in the x direction. Now this more closely would fit to having some sort of wind pushing with the direction of motion of the rover, and therefore that when the rover lands, it has to oppose that by going the opposite direction. So this is assuming going to the negative direction would be going back on itself. And for t, because of its relationship to time, this is half. T represents half the total time to t. So t is half the time it takes to get halfway, or no, it's the time it takes to get halfway.
Moving into the movement in the x direction, we graphed this on Decimas, where we have our vertical line marking the launch, which just represents negative t, and then our second vertical line representing the landing, which represents t. I'll first reference our purple function, which is the position, the graph of position over time. And what this shows is at the points of launch and the landing, where the change in the position over time is 0. That just means that we are not going to be increasing how we're moving. And so from launch negative t, we have a quick increase to a constant steady movement. And then at point 0, which is in between negative t and t, the halfway point, at that point, we move from that steady towards a decreasing position over time to then going into a flat point, where that flat point that just continues to go marks that we are no longer gaining distance, in the X direction. And then this, the graph models as Y increases, the helicopter is moving positively in the X direction. And then moving to our velocity graph, which is the blue graph, what this shows is at point negative t, our velocity increases to that point 0, which is our halfway point, and that marks our maximum velocity, and from there our velocity increases back to 0. So that's just saying that our helicopter is moving and it speeds up to a certain speed, and then once it hits that speed, it starts to slow down, but velocity for this whole entire point remains positive, so we know it's going to always be moving in the X direction. And then moving into acceleration, our acceleration shows that we have an instantaneous positive acceleration that decreases over time, only becoming negative at the halfway point, which would make sense because at that point where acceleration becomes negative, then our velocity graph would start decreasing down to 0. And then just real quick, why this makes sense with our distance equation, distance of x is equal to 2 beta times t squared over 3. This makes sense because if we increase the distance, well, if we spread out t, so if on the graphs it shows t is equal to -2, and then negative t is equal to -2, and then +2. If we increase this, then that means we're going to have to increase, the distance is going to increase, and then beta, the scalar for acceleration, says that if we increase beta, which is just going to increase our initial instantaneous acceleration, the increase in displacement, there will be an increase in displacement.
All right, for the movement in the Y direction, it's very similar to that in the X direction. However, the one difference is that if we look at the position function that is in purple, it quickly gains altitude, and then it'll level off. So it'll be loitering for some time around t = 0, and then after some time again, it will then gain altitude before landing right at the apex. We could see that in the velocity function pretty clearly, how it gains a lot of velocity and then it slowly loses its velocity until it's just not gaining or losing any altitude and loitering at t = 0. And then similarly in the acceleration, we see a big spike in acceleration that rapidly decreases. This is fighting back against the planet's gravity, and then it goes down negative as it decreases velocity until it reaches 0, and then has to quickly gain some acceleration again as it makes that final climb back to it, or to its final landing spots.
Moving into time of flight, this is real simple. This is just finding our change of time, t final minus t initial. We know t final is equal to t initial is equal to -t. So our change in time, which is equal to our total time traveled, is going to equal to 2t. And then from there, we're just plugging in the prescribed our prescribed t equation that we derive from the distance in the x direction. So once we do that, we just get 2 times the square root of 3 times distance over 2 times beta, which gives us the entire time of the flight.
Yeah, so here we have the motion of the rover, and in this, so we start at t = -t and then ends at positive t. The important thing to note here that is the helicopter's midway point at t = 0, both in the x and in the y directions. Next slide. So for homework 2, activity 3, the important thing, it's asking for a distance in between the stop signs. And in this, we need to find the pause or the acceleration, velocity, and position functions as graphs, and it gives us constants of velocity and time, and which change the end result when adjusted. For help practice 2, problem 3, it asks for the distance until rest of the large cylinder rolling down and slowing due to air resistance and friction. And in this also, it asks for the acceleration, positive or position and velocity functions. And it has constant predetermined variables. And then the last is the Mario problem, which Mario runs at a constant acceleration, determines with the determined acceleration function. It asks for the time to return back to the original velocity and the position related to time, and also, but it has undetermined variables, which differs from the others. And it also asks for the position, velocity, and acceleration function or graphs.
Thank you for your time. This concludes our presentation.